Okay, this is a video on section 12.4 from the book. This is talking about a thing called permutations. A permutation is an arrangement where order matters. What this is essentially saying is how many ways can we organize something? And I like to really think about ice cream when I'm talking about permutations. Not just because it's a nice example, but because ice cream is good. So let's talk about ice cream. Let's say you walk into 31 flavors. Hopefully you guys have 31 flavors around here. Their big thing is that they have 31 flavors of ice cream. Okay. This is also called Baskin Robbins sometimes. Baskin Robbins. This is the ice cream place that was around my Sebastopol. Okay. So 31 flavors. They have 31 flavors. Let's say you're going to go in and you are going to order a triple scoop. Okay, well, the question becomes how many different types of ice cream, how many different permutations of ice cream could you order? Because we know that, let's see, just sticking with the basics, chocolate, vanilla, and strawberry. This is one way you could get it. But let's see, vanilla, strawberry, and chocolate is a very different thing than chocolate, vanilla, strawberry. On this one, vanilla is the top scoop. Chocolate's the bottom scoop, right? This is a different permutation, okay? But let's see, what happens if you want mint chip, peanut butter, and I don't know, what was that? Daiquiri ice. Ugh, that flavor's gross. If you want this permutation, right? This is different than, say, getting peanut butter, chocolate, and then vanilla, or even getting peanut butter, vanilla, then chocolate. These are all different ways that you could order your triple scoop. Okay? So mathematically, the way we think about this is, let's see, you're going to get 3 scoops, okay? So here's 1 scoop, 2 scoops, 3 scoops on your cone. Okay? How many choices do you have for the top flavor? Well, let's see. You have 31 choices, okay? Let's see. How many choices do you have for the second flavor, given that you're going to get a new flavor? Let's see. You're going to have 30 choices. And then what about for the last flavor? How many flavor do you have to choose from? Well, you have 29 more flavors, okay? So to find out how many you actually have, you have 31 times 30 times 29, okay? If we wanted to change the situation, okay, let's say that we have a new store that their big thing is that we have 51 flavors, okay? And same thing, you want to come in and get a triple scoop with 3 unique flavors, okay? How many choices do you have for the first one? Well, you have 51 choices. How many for the second scoop? You have 50 choices. How many for the next scoop? You have 49 choices. Okay? So this is how we would be thinking about it and multiplying our numbers together to find out how many are actually available to us. Okay, so sticking with our ice cream, okay? Let's see, we're at 31 flavors, and you're still going to get a triple scoop, but you want chocolate on top and no repeat of flavors. Okay? Let's see, so if you want chocolate on top, how many choices do you have for this top cone? Well, chocolate is your only choice, so you have one way of choosing chocolate, and that is by choosing chocolate. Okay? But then the same idea continues. How many choices do we have for the second scoop? Let's see, we have 30 choices. Okay? And then how many ways could we get the first scoop? Well, there would have been 29 choices available to us. Okay? Then we would just go 1 times 30 times 29, which will give us our number of how many ways we could have gotten ice cream from 31 flavors with chocolate on top. Okay, this is another example of the type of problem you might see. This is saying that a permutation is selected at random from the word sequoia. So what it's doing is it's taking these letters and it's creating a permutation using them, and it's asking you to find the probability that Q will be in the 4th position and that there'll be a vowel in the last position. Okay, so how many words or letters do we have? 1, 2, 3, 4, 5, 6, 7. Okay, so this stuff is going to be 7 letters long. So 1, 2, 3, 4, 5, 6, 7. And we have to have a Q in the 4th position. How many ways can we have a Q? Well, there's only one way to have a Q. Okay. Followed up with there has to be a vowel in the last position. How many vowels are in sequoia? Well, let's see. We have 1, 2, 3, 4, 5. We have 5 different ways in which we can choose the vowel. So we'll put 5 in the last position. This leaves us with how many choices do we have left? Well, we've already chosen 2 from our 7, so we have 5 choices left. So there's 5 choices here, followed by there's 4 choices for here, 3 choices for here, 2 choices for here, and 1 choice for here. Now all we have to do is go through and multiply this all together. Okay, and this will give us the number of arrangements for our special condition. So we'll call this our condition C. Okay, but it's asked for probability, and probability has to be portrayed in some type of ratio so that we get a decimal. Okay, so we have to compare to this to what is the sample space to this problem, which is essentially just asking how many different ways can we make a permutation using these letters. Well, how many choices do we have for the first? We have 7. How many choices for the second position? We have 6. How many choices for the third position? 5, 4, 3, 2, 1. This is going to give us the number of our sample space. Okay, so I went and grabbed a calculator, did this. So for matching, the permutation for matching our condition was 600. Okay, there's 600 ways in which we can have a Q in the 4th position and a vowel in the last position. The permutations altogether of just arranging the letters of sequoia, okay, that's our sample space, and that's just 7 factorial. If you notice, this is just 7 times 6 times 5 times 4 times 3 times 2 times 1, which is the definition of 7 factorial. This gives us 600 and 5,040. So to get our probability, we are just going to divide these two numbers. This is our the number of our conditions divided by our sample space. So 600 divided by 5,040 gives us 0.1190. Okay, 0.1190. Okay, which if we change this into a percentage, this is saying that 11.9%. Okay, so 11.9% of the time that you select a permutation created by the word sequoia, okay, 11.9% of the time you'll get a Q in the 4th position and a vowel in the last position. If we try and put this in terms of numbers we like, let's think that if you selected 100 words, okay, if you selected 100 words from the permutation of sequoia, roughly 12 of them should match our condition. Okay, so what I'm saying is that if we selected 100 words at random from a permutation of sequoia, okay, 12 of them should have a Q in the 4th position and a vowel in the last position. Okay, these are the type of problems we'll be doing with permutations. If you have any questions or comments, please let me know, and I will see you all tomorrow in class.